So I'd like to start with the positioning and the intended audience for this course. This is meant to be a basic course on engineering electromagnetics. It is focused to students of electrical engineering. Here in IIT Madras, we typically teach this in the second year, and I assume that practitioners in the field of electrical engineering may also find some use to some of the content in this course. I am assuming that some high school level physics is known to the audience, and other instructors in the colleges of this country may choose to appropriate content from this course where they see that their current syllabus might be missing. The structure of this course is as many of the online courses. It's going to be video lectures where I mostly handwrite on a tablet PC in front of me, and the course content is very similar to many of the instructors that have come before me to introduce this topic. Many stalwarts have taken up the responsibility to teach engineering electromagnetics for undergraduate. So you might already find a lot of content online. Nevertheless, we will try to give the same flavor and try to make sure that we are more pertinent to the field as it is today. Okay, perhaps give some more examples that are more typical of what you might see in a job today. So we will use the method of transmission lines to introduce the concepts of electrodynamics. So the syllabus can be split into 4 main topics. We will start with a quick comparison of electrostatics and electrodynamics. Electrostatics is mostly what is covered in your high school and perhaps also in your first year science courses. So in order to make the transition smooth, and so you see the connectivity between what you have learnt already to what is to come, I believe the first unit can try to put all the audience on the same page. And then we will look at transmission lines and try to introduce the concepts and the mathematics behind electromagnetics, which is the Maxwell's equations, from the viewpoint of transmission lines. And then basically try to expand the relevance of what we have learnt from transmission lines into more broader situations, right? So for anyone starting on this course, the question that comes most often to a student is why study this subject, right? So I have listed down 4 likely things that might inspire you to take up this subject, right? First, I have always felt nature is an excellent form of inspiration. Okay, so to just look at the world around us and see how it functions, how it works, gives a lot of inspiration to many of the scientists and engineers today, right? So a lot of the natural phenomena like rainbows and lightning, mirages on roads, the fact that magnets of the same polarity when brought close to each other repel each other, whereas the opposite polarities attract. These are some phenomena that obviously raise curiosity in most people, right? So this course will certainly give you a bit more deeper insight, right? As many engineers share this opinion that a deep physics knowledge of what happens in the nature around us only increases the interest or the level of enjoyment that you get out of these phenomena, right? It never subtracts. So, the beauty of a sunset is only enhanced by knowing what is the physics that governs the spectacular nature of what we see, right? And a second viewpoint is perhaps you are not a big nature lover, but you are certainly very fascinated with the modern conveniences and the modern gadgets, right? So, perhaps you don't even have to go that far back in the history, right, to kind of view what the situation was like for human beings and how the daily chores have significantly changed, right. So, the modern day appliances like microwave ovens, cellular phones, satellite communication, right, self-driving cars, augmented reality and virtual reality headsets that are coming from various companies, and even perhaps in the field of medicine, we notice that we use fairly expensive, fairly complex equipment, right, to diagnose disease, right. So, engineering and specifically electrical engineering has played a big role in a lot of what we can be proud of as humanity, which is the level of poverty and the mean expectancy, life expectancy of human beings have all seen an improvement steadily in the last few decades. And I think we can certainly attribute some of it to very skillful electrical engineers in the past. And engineering electromagnetics, I am sure if you asked any of those engineers, would have been a key subject for these engineers to have achieved what they have achieved, right. Another third perspective is perhaps more job centric, right. So, perhaps you are not into the first two bullets, but if you are more focused on the jobs and what kind of work can I get, what kind of salary I can get, even in that perspective, I believe that there is a shift happening, right. So, I believe future jobs, which is what you young students should be looking forward to, requires skilling of a different nature, right. So, the knowledge of electromagnetism in most modern day jobs requires you to know some amount of electromagnetics, right. Perhaps we have seen a few decades go by where the knowledge of electromagnetics perhaps in certain areas were not as critical, but we are starting to get to the point where we are facing the limits of what we can do or what nature allows us to do. And in these realms, right, at very small nanoscopic levels, the field of electromagnetics is getting a certain resurgence, right, and a knowledge of it is very critical. Okay. And a fourth and final way to look at this is engineering electromagnetics is perhaps at the most foundational level of electrical engineering, right. Although you can claim to say that quantum electrodynamics is the best known effective theory developed by physicists to understand electromagnetic waves and its interaction with the matter around us, for many situations, right, a good majority of them, especially when it comes to practical electrical engineering, we notice that classical electrodynamics is sufficient, right, and provides a very good foundational understanding, and it's easy to go from here, right. It's always easy to climb up the stack to go from the electric fields and magnetic fields, all the way up to currents and voltages in circuits and all the way to systems, right? And characterization and experimenting with these subsystems and modules. So, one thing that I can promise you is the journey is going to be fairly exciting. The class is going to stretch your conceptual abilities, right? And this is perhaps the closest thing to magic that you can probably see, because we are essentially dealing with the core workings of the nature, right? So, as I said in the first bullet, electromagnetism is one of the 4 fundamental forces that we observe in nature, the other 3 being gravitational forces and internal forces, nuclear forces, strong nuclear force and the weak nuclear force. So, with this kind of a motivation, let us move to a particular exercise that I am very fond of. So, this was introduced to me in my elementary school, and it is something that has captivated me since and has given me a very good outlook each time I am faced with something very new, right. So, the exercise is called See, Think, Wonder. I am sure you can all read up about it yourself as well. Maybe you are fortunate to have teachers or instructors in your high school or elementary school who actually used it as part of their instruction. So, in electrical engineering, it is always good to not just open up a box and electronic equipment and say that it is made up of all these things, right, but to actually look at them and look at them closer, right. And this exercise of See, Think, Wonder is a good way to sort of exercise your creative senses to actually ponder on why they are the way they are, right. So, essentially See, Think, Wonder involves 3 activities. So, given that this is an online course and I do not have personal time with each of you, this is something that I routinely run in the class, but I am sure you can also do them individually. So, you can pose yourself a certain picture, a circuit schematic or a diagram or a system or any object for that matter, a piece of technology, and I would like you to ask yourself these questions and try to answer them yourself, right, and perhaps share it with any of your classmates if possible, or your local instructors when you get a chance to meet them, or perhaps even if there is a live session in the future with me, maybe we can try to dedicate some amount of time for this kind of a session. The reason to do this is also that it kind of slows you down, right. One thing is people are in a hurry to sort of gather the information there might be and perhaps end up with a superficial understanding, right. So, I think this exercise essentially stops and helps you think for some time. It tries to bring in the distinction of what you observe versus what you interpret, right. These are often 2 distinct things, and often we try to cloud these 2 by trying to make quick assessments and judgments, right. So, trying to distinguish them as 3 individual blocks, you can even take a piece of paper, have a box each for what you see, what you think and what you wonder, right. In fact, I am going to flash some sample images, and I hope you can pause this video appropriately and try to do the exercise, right. So, I see is mostly an observational skill, right. So, you just merely list down what you observe in the picture that is in front of you. You are not making any judgments or assessments as yet, okay. And then you can transition to what you think the circuit might be doing, or what you think is the purpose of all the elements within the object. And then finally, you could wonder how they actually work together, or perhaps even wonder what other information you would like to know that is beyond the picture, for you to perhaps make the connection to something that is more practical, or maybe how it is used in the real life, okay. So, let us take an example. So, if I flash you an image, right? This is a product that is available that you can buy, and if you say open up one of these boxes, I find a PCB board, and these are the front and back view images of this PCB, right? For someone who is coming from high school, this is not how you expected to see your circuit designs, right? Despite the fact that you might see some elements that you may relate to as so-called lumped components like resistors, inductors or capacitors, what may come to your mind are the way these so-called copper traces are laid out, right? They seem to have certain thickness. Thickness seems to be an issue. What I mean by thickness is this dimension, right? Because in certain places the traces seem very thin, and certain places they are fairly large, right? I also see some interesting shapes, right? I notice that in some places there are tiny bridges, and in some places there is an entire gap. Okay. You might ask, this almost looks like an open circuit at this point, right? So you may even wonder that does this even function if all the elements are not even connected to each other, right? And looking at the back side, we also see some more interesting features. We again see the variation in widths. We notice some bending that may or may not have been required. We look at very interesting geometries and shapes. We have a nice perfect square here, but somehow this line here seems to be isolated going into this square. You may wonder why that is the case, and also that there are two copies. This seems to be a replica from the left to the right, right? So here are some things that you can do as an exercise, right? So remember, these are circuits, okay? These are circuits that were designed by electrical engineers, like who you choose to aspire to become in the future, right? Which means you need to know what it takes to make some circuits like this, right? So another thing that you can do in See Think Wonder is not just stop at being shown images, right? Sometimes you can also introduce the context, right? And then again revisit the See Think Wonder, right? So if I told you that this is a PCB, what you saw in the previous slide, and the size of it was only the size of a coin, okay? So that puts a perspective to how big that really was in the previous slide, right? So these are extremely small objects, right? Now the question is that size of the object important? Perhaps it is, right? But it throws a new perspective, right? And I am also going to tell you that this product is a product that measures the movement, or it is a velocity sensor, right? It is able to detect when an object is placed in front of it, and when it is functional, is able to tell whether that object has begun moving and how fast is it approaching, right? So it is based on a idea called Doppler radar, okay? But now that I have given you this information, you can always revisit those images and ask yourself the question, what do you now see, or what do you now wonder about the PCB design, right? So I hope that at least from a very cursory standpoint, you understand that printed circuit boards are some sort of a highway, right? You can picture them like that, right? Picture them as highways for carrying electrical signals, and that one can have three-dimensional structures just like flyovers in order to be able to carry in the same locality or the same spatial area many electrical signals by stacking them vertically, right. So, that is one of the reasons for the printed circuit board technology. So, you can see that even though this was the entirety of the circuit that I wanted to build, I kind of divided them into segments and realized some segments on one side of the printed circuit board and perhaps some of the other elements on the other side of the printed circuit board in the interest of miniaturizing the product, right. All right. This was one example from Doppler radar, which we call as an analog system. There is also the counterpart in digital data communications. You might say that I work in the field of, or I am interested in the area of AI or machine learning, which deals with a lot of digital data communication. Even in those areas, we notice something that is a bit out of the ordinary form of drawing circuits, which you are traditionally used to, where I can draw a battery, say a resistive load, an inductor, a capacitor. This is how we are used to drawing circuits, right, using lines, and we connect them all together, and we do not quite emphasize any importance to how long or how big your circuit is, right. The functioning of the circuit is more to do with the elements and how they are combined with each other rather than how far apart they are, right. But we will notice that in this course that perhaps that is not entirely true in all situations, right. So, one thing that you might ask looking at this image, which is a printed circuit board that is trying to route a lot of digital data or digital signals, is why are these traces so wavy or curved, right. You can notice that there might be a much more elegant route from this particular port to the left, right, but it seems to meander like a river around, right, and it seems to be doing some funny business, right. You might notice some simple notches that seems to be out of place. So, you might naturally think why or how one goes about doing this. How does one design that I need to turn this many turns, or this is how I should lay it out, right. So, here is another observation, right. As an electrical engineering, I am going to give you an example again in the land of high speed digital data communication. I am essentially trying to communicate something from this point A to this point B, and this is a picture, a cross section of a printed circuit board, okay. And it is showing you that there are 4 layers, layer 1, layer 2, layer 3 and layer 4, right. And I merely have indicated in black, which essentially is copper, a very good conductor or a conductive metal, that is essentially connecting the points A and B, okay. But it does so by actually boring a hole through the printed circuit board, which is called a via. And I notice that if I were to send a signal that looks like this single pulse, and if I were to monitor this pulse at the end at point B, I notice a shape that looks very different, okay. This is not what I expect out of a simple wire, right. So, if I were to connect 2 points, I expect the 2 points, the end points, to have a faithful reproduction of the signal that might be at the beginning of the wire, right. So, if I have a good conductivity wire, and if I were to just join 2 points in a circuit, this is what you would call as an electrically short, right. So, points A and B are electrically shorted, and in most of the circuits that we have been taught so far in schools, we are expected to believe that whatever happens at A should be faithfully reproduced at B, right. But somehow if I were to do this experiment in a lab, it's not even a very special case, right? And this is something that you can quite readily observe, right? So, what are the things I can observe? One is, even though there are no scales on the two images of the oscilloscope data, we can say that the pulse is stunted, right? So, the height has reduced. Another thing you can say is the pulse has also broadened. Okay. Some observations that we can make are the pulse height seems to have reduced, the pulse width seems to have broadened, and I also seem to notice that it takes some time to kind of get to these different voltage levels, right. My intent was to just send a low voltage signal and a high voltage signal for a brief period of time and then come back down, right. But it seems that even though if I condition my signal to make these transitions reasonably quickly at the beginning of this wire, by the time it reaches the end of the wire, I notice that it has been distorted, right, quite significantly. So, we have to understand, and we need a very simple method to say how can I understand this transformation. And beyond understanding, we need to go to actually being able to quantitatively say that if given a certain characteristics of a signal at the input of the wire, what are the characteristics at the output, okay? And this course will help you with that. So, this is a point where I want to kind of remind you, right, that reality seems to be described by laws that are mathematical. Okay. So, mathematics is inevitable in understanding a lot of the concepts that I have gone across before, right. So, to a lot of modern day engineers, right, the important question is what is real or what is not real. That is not the important question to them. Okay. What is really important is how do I make use of how things seem to behave, right, rather than trying to alter its nature. I would like to study and get to know the limits of the behavior, right. So, I need to be able to make my calculations or predictions of when I make a new system as to how it will behave, right. So, that seems to be more important to engineers today than to ask if the notions or ideas. So, we are going to come up with a very key idea that I am going to shortly talk about. You might even get to a point in this course to ask, are these even real, right. So, just remember that whenever such things come to your mind, that perhaps as an engineer, we lay less emphasis on whether these are actually true objects that I can sense or not, but rather have the comfort that we have this powerful mathematical toolbox, right, that actually helps us understand the reality around us, right. In this context, I always encourage budding engineers, new students to read this article in your free time, right. It is not a very long article, but please, if time permits in your schedule, try to take a look at this. It is not a very recent article, it is a reasonably old article written by Eugene Wigner as to the unreasonable effectiveness of mathematics in describing physical laws, right, and the nature around us. This has always intrigued me, right. Why is so many of the things that are around us seem to be so well modeled, right, or it seems to be so highly mathematical, okay. And I think the article will give you a good insight, right, a nice perspective. So, I talked about Maxwell's equations. So, certainly James Clerk Maxwell, the scientist who has been credited for a lot of the underlying mathematical formulations for engineering electromagnetics that we use till today in classical electromagnetics. he has been deemed as the shift in our view of how electromagnetics and the electromagnetic force works in reality, right. So, when asked two very well known scientists, one is Einstein, about Maxwell's discovery and its implication, right. Here is what they had to say. Since Maxwell's time, physical reality has been thought of as represented by continuous fields, okay, governed by partial differential equations and not capable of any mechanical interpretation. Okay. So, this was his view, and in another excerpt from another very famous scientist, Freeman Dyson, he had this to say about Maxwell's equations, right. The idea that primary constituents of the universe are fields did not come easily to physicists, right. So, you shouldn't feel any different, right, when you find the concept of fields when it is introduced in this course, that it is a little hard to wrap your head around, because this is something that every physicist, every engineer has had to go through, right, including me. Fields are a very abstract concept, right, far removed from the familiar world of things and forces that we are used to, okay. But nevertheless, it is one of the basic natural forces, right, and fields are a way for human beings to communicate scientifically amongst each other. So, what are these fields? I really hope that you are not thinking of the fields in its most commonly used sense, like an agricultural field. The field that I am talking about is something quite different. So, we will take this up from the next class. We will try to understand what these fields mean in the context of electromagnetics and in the context of circuits and so called transmission lines, and we will try to develop this concept in a step by step fashion, so that you feel at ease as you are progressing through this course. Thank you.